This is Math341, Lecture 22. So today we're going to talk about various types of generating functions. And before I go into all the details about all the different types of generating functions, I want to at least motivate to you why we have so many different types of generating functions. In some sense, a lot of them are equivalent under a change of variables. So it's all about algebra. And one of the big lessons in life is, depending on how you look at things, you can make the algebra either a lot more pleasant or a lot worse. So consider the following. 11 minus 3 plus 17 minus 11 plus 88 minus 17 plus 112 minus 88 plus 2010 minus 112 plus 4003 minus 2010. What does this equal? 4,000. Who said that? Excellent. How'd you get that so quickly?
Because everything cancels out except for the top.
Everything cancels out. Right? This is a telescoping sum. Where have you seen these before, or at least where should you have seen these before? So you should have seen them in a calculus class proving the fundamental theorem of calculus, that the antiderivative at b minus the antiderivative of a is the area under the curve. It's one of the best applications of telescoping sums. Could you have calculated each row and then added the results? Absolutely. But it's a lot more work. And if you have a very complicated expression, it's going to be hard to realize what's going on, and you might not see some of the cancellations if you have very complicated expressions. This is the main point to keep in mind for today's lecture, is it's all about trying to find which way can we write the things to maximize your chance of seeing what's going on and to minimize the amount of painful algebra you need to do. Some things just work better for the algebra than others. It doesn't matter which one you use in some sense, and in another sense it absolutely does matter, and if you choose the wrong one, it's a nightmare. So we're not going to do too much with the following, but I want to just briefly mention. Let's say x is a random variable. I could define a function px of x to be the sum, say n goes from 0 to infinity, the probability x equals n times x to the n. So we'll assume here x is discrete. If I have another random variable py of x, I would have the sum, let's say n goes from 0 to infinity, probability y equals m, x to the n. And I could look at the probability, this function px of x times py of x. So I probably should have used a different variable, probably t, but it doesn't matter. So I'm going to have to multiply everything out. So let's just call the first one, an x to the n, and the second one, b m x to the n. And I want to multiply them out. So if you want to write it the long way, it's a0 plus a1x plus a2x squared plus dot dot times b0 plus b1x plus b2x squared plus dot dot. How can I get a constant term?
B0, B0.
That's the only way, is A0, B0. How can I get an x term?
A0, B1x, B0, A1x.
Good. A0, B1 plus A1, B0 times x. How can I get an x squared term? So how can I get an x squared term?
B2, B0.
Let's start off with A0. A0,
B2.
A0, B2. What's the next one?
A1, B1.
A1, B1.
A2, B0.
A2, B0. I'm not worrying at all about convergence. Do you recognize what these numbers are? Where have we seen something like this before? For this particular problem, it would be the sum, k goes from 0 to infinity, the probability x equals, or let's do it this way, x plus y equals k, x to the k, and that's the longest sum, the sum k goes from 0 to infinity, the sum L goes from 0 to k, the probability x equals L times the probability y equals k minus L times x to the k. It's the convolution. That how do I get the x squared term? 0 plus 2, 1 plus 1, 2 plus 0. Oh, that's all the ways x plus y could equal 2. So if I take as a function something like this, where the coefficient here is the probability that x equals n, if I have two independent random variables, the product is going to be very nice. And what's lurking in the background is the convolution. It turns out that this is not the best one to study, in part because most random variables are not discrete. We have a lot of continuous random variables. So we will start looking at generating functions. And the first one will be gx of s is equal to the expected value of s to the x. And if it's discrete, that's going to be the sum, n goes from 0 to infinity, the probability x equals n times s to the n, if discrete on the non-negatives. So a lot of random variables are discrete and take on only non-negative integer values. So this is an extremely important special case. More generally, it's just the expected value. So we would have to sum over all possible values, or we would have to integrate. Okay? This is very similar to what we had here just a moment ago. Right? When this is discrete, all I'm doing now is I'm using the letter s rather than the letter x. And so we've got as a fact, if discrete and independent, then the generating function of x at s times the generating function of y at s is the generating function of x plus y of s. The main goal we have is we can do two things. Given x, we can find g of x. Or, given a g, find the corresponding x. So the question is, if I give you a generating function, does that uniquely determine a random variable? This is going to be essentially how we're going to try to prove the central limit theorem. It's going to be a generalization of generating functions, and the goal is to show that it's converging to the generating function, or the generalization of that, of the normal. And then what we would love to say is, well, if it's converging to the generating function of the normal, it must be a normal. Unfortunately, it's not always the case that you have this one-to-one correspondence. Sometimes you could have two different things mapped to the same thing. For example, let's say I have f of x equals 3x plus 8. And I tell you y equals 11. What does x equal? Yes. 1. If I tell you y equals 14, 2. This is not particularly challenging, right? In this setting, if I give you any value of y, there's a unique x that corresponds to it. Now imagine I give you g of x is x squared. And I give you y equals 0. What does x equal? Oh, good, so it's the same as before. Everything is unique. No. If I give you now y equals 1, then you get x is either 1 or minus 1. There's not a unique output. And that's the problem. So for a lot of the stuff, it's not going to be the case that there's a uniqueness. Now, what could we do to make this unique? We don't view this as a function on all the reals. View this on the set of all x greater than or equal to 0. If you viewed it like that, then it would be unique. And every output would then have a unique input. So it's just nice to know where the pain is going to come from. All right, so returning to generating functions, we know that if they're independent and discrete, non-negative, then the generating function of the sum is the product of the generating functions. Does this remind you of any results you've seen before? Not exactly, but somewhat.
Properties of exponents.
Properties of exponents, right? And you can talk about group homomorphisms if you take an abstract algebra in terms of how you change the multiplication symbols and whatnot. But the generating function of the product, the generating function of the sum is the product of the generating functions. All right. It would be wonderful if the generating function was uniquely determined. And so we do have if x and y discrete on the non-negative integers, and the generating function of x equals the generating function of y, then x equals y. This is a wonderful special case. So if we want to try to figure out maybe what a sum is, if we can figure out the generating function of x plus y, and if it agrees with that of a discrete non-negative, then we're done. So if you recall, at the end of last class, we did Poisson plus Poisson, and we got a Poisson. This is going to be another way to do that without having to do the terrific insight of I multiply by this and divide by that, so multiply by 1, I pull this out, I recognize this as a binomial coefficient, I use the binomial, without having to do all of that. It makes it more formalized. So the proof, there's two ways to go. One is if you are allowed to differentiate, you can just take the nth derivative set to equal to 0, and then notice that the coefficients must match. Because we know gx of s is the sum, the probability x equals n, s to the n. Gy of s is the sum of the probability of y equals n, s to the n. We would like to say that the only way these two infinite series can be the same is if all the coefficients are the same. And if you can just differentiate term by term, take 5 derivatives, set s equal to 0, only the n equals 5 term survives, and they must be equal. But now you have to justify differentiating an infinite series. So if you feel a little bit uncomfortable with that, take s equals 0. So when you take s equals 0, only the first terms survive. And that implies the probability x equals 0 is the probability y equals 0. Now, study gx of s minus the probability x equals 0, and what should I divide that by? So I subtract off the constant term. What should I divide it by?
1 power of s.
1 power of s. And so now the first term of this is going to be the probability x equals 1. The next term will be the probability x equals 2 times s. The next term will be the probability x equals 3 times s squared. And so now this is going to be the same as gy of s minus the probability y equals 0, because they're the same, over s. And now we're back in the case of we have two infinite series. And all we have to do now is just take s equals 0, and we get the constant terms must match. And then just lather, rinse, repeat, and just march down. So if you have discrete non-negative random variables, if the generating functions are the same, then they are the same random variable. It's a way to identify what do you have. So if you unsure what random variable you have, if you can compute its generating function, you're in great shape. All right, let's do an example. Let's do x's Poisson with parameter lambda. So the probability x equals n is e to the minus lambda, lambda to the n over n factorial. Question?
Is it also n equals 0? Or no?
No, this is taking n equals 0. So we're looking at what's the probability x equals 0, what's the probability x equals 1, what's the probability x equals 2.
Okay.
So this will now allow us to get that the probability that x equals 1 is the same as the probability that y equals 1. Because what's really happening here is, I'll erase this part. We subtract off the constant term. So we initially had a sum from 0 to infinity. Now we have a sum from 1 to infinity. And now since we pull out an s, we have an s to the n minus 1. And so when you expand that out, you'll then get the probability x equals 1 plus the probability x equals 2s, and so on and so on. And now since that equals the same thing with y's, now we'll get the probability x equals 1 is the same as the probability y equals 1. And then you just keep marching down like that. Okay. So let's take x's Poisson. So we want to calculate the generating function of x. So this is going to be a sum, and it goes from 0 to infinity, of the expected value of s to the x. So it's going to be s to the n times the probability x equals n. So this is the sum, n goes from 0 to infinity, s to the n, e to the minus lambda, lambda to the n over n factorial. What should I combine? S and lambda. They're both being raised to the nth power. So if we combine them, this is going to be the same as the sum. N goes from 0 to infinity. I can pull out the e to the minus lambda. And I'll have an s lambda to the n divided by n factorial. But what is this whole expression here? That's just e to the s lambda. So we get e to the negative lambda, e to the s lambda. Or this is e, and there's two different ways to write it. I want to write it as s minus 1 lambda. So we have the generating function of the Poisson. Okay? So just, here's the definition of the Poisson, here's its probability, here's the definition of the generating function. We do the algebra, we get the following. All right. Let's now look at Poisson plus Poisson. So now let's say x is Poisson with parameter lambda 1. Say x1 is Poisson lambda 1. x2 is Poisson with parameter lambda 2. So the generating function of x1 plus x2 of s is the generating function of x1 of s, the generating function of x2 of s. Okay, so we get e to the s minus 1 times lambda 1, e to the s minus 1 lambda 2. The algebra should be screaming at you what to do now, right? Add the exponents. And you get e to the s minus 1 lambda 1 plus lambda 2. But this is the generating function of a Poisson with parameter lambda 1 plus lambda 2. So now we can conclude that x1 plus x2 is Poisson with parameter lambda 1 plus lambda 2. Because x1 and x2 both take on non-negative integer values, their sum will take on non-negative integer values. We've shown that the generating functions in such cases are unique. And so now we know Poisson plus Poisson is Poisson. So in some sense, the Poisson is a stable distribution. When you add a person to a person, you still get a person. This is similar to if you add a normal to a normal, you get a normal. If you add a Cauchy to a Cauchy, you get a Cauchy. Oh, is it the case that your shape never changes? Can you give me an example where your shape changes? Uniform. Uniform plus uniform is definitely not uniform. All right. So let's look at the generating function of an exponential. And we will see that the generating function of exponential is enough to let us know that very different behavior can happen. Now, we do not have the same theorem in the continuous case as we do in the discrete case. In the continuous case, it is not a fact that if your generating functions are the same, you are the same. I've done the Taylor series of this function e to the negative 1 over x squared if x is not 0 and 0 if x equals 0. We've talked about this function. I think we've mentioned this. Have we mentioned this in class? That all of the Taylor coefficients of this function are 0. So you have to use L'Hopital's rule. And so if you do the calculation, you get the nth derivative at 0 is always 0. So if you write the Taylor series of this function, it's identically 0. This function has tremendous decay near the origin. If x is 1 over a billion, you get e to the negative billion squared. This is small. So this function, its Taylor series expansion, is identically 0. That means it only agrees with the function at the point x equals 0. The hope is that if you have a nice function, the Taylor series converges to the function as you take more and more terms. No. It only agrees with the function at x equals 0. This is really not something to celebrate because the Taylor series is f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial. Everything from here onward has an x. So when you put an x equals 0, these all vanish. You have to agree at 0. And that's the only place where it agrees. It's because of functions like this that real analysis is hard. Complex analysis is actually a significantly easier subject because complex analysis does not let functions like this in. This function is real differentiable. It's infinitely real differentiable, but it is not complex differentiable. In fact, it's not even continuous in complex analysis. And because of that, a lot of these bad counterexamples do not exist in complex analysis. That's what's really lurking in the background. But because functions like this exist, we have to be very careful in the continuous setting. So, continuing with our generating functions, let's now do an exponential. So let's say x is exponential with some term to lambda. All right. So let's calculate the generating functions. We get the generating function is equal to the integral from 0 to infinity of s to the x e to the minus lambda x times lambda. Oh no, I do x over lambda. Sorry. Right? I do x over lambda. Times dx, and I have a 1 over lambda. So that's my exponential density. So I need to do this integration. So the question is, will this converge? How should I write s to the x? What kind of function is s to the x? It's an exponential. It's an exponential base s. Thou shalt not use base s. Okay, what bases are acceptable? E. What else? Nothing. Right? When you're doing pure math, it's base e. It makes it really easy. Does the universe care that we have 10 fingers? Probably not. Right? I cannot prove that the universe does not care that we have 10 fingers. I think as a working assumption, the universe doesn't care that we have 10 fingers. Base 2 is very natural for computer science. And in fact, in computer science, logarithm is often base 2. But for us, it's always base e. I can write this as e to the x log s. And if you're not sure if this is correct, take the log of both sides, and you'll get s log s is equal to x log n. Good. So now, our generating function is the integral from 0 to infinity. I'll pull out the 1 over lambda, and we will have e to the x log s, e to the negative x over lambda dx. All right, so if I just pull and combine, I get e to the negative, I'm going to write it as 1 over lambda minus the log of s times x dx. What do I need for this integral to be well behaved? So if I want this integral to be finite, what must be true about this number in parentheses? It must be positive, right? If that number in parentheses was not positive, then this would be exponentially growing. So we always want to make sure that we're working with things about parentheses. We need 1 minus lambda, 1 over lambda minus the log of s to be greater than 0, or we need the log of s to be less than 1 over lambda. So that makes sense. As long as s is not too large, we're going to be fine. If s equals 1, we should be okay. If s is less than 1, we're even better. So this gives us the range at which we expect it to work. So it's not always going to be the case that the generating function exists for all inputs. It might only exist for inputs in some range. And that will be a bad complication later. All right, so now when you look at this exponential over here, this almost looks like an exponential random variable. And so if I just accept, of course, it's defined the wrong way. I prefer to have this in the denominator, but that's fine. So what we can do is we can say this is the expected value of f, generating function at s is 1 over lambda, integral from 0 to infinity, e to the negative 1 over lambda minus the log of s times x. Then I multiply by 1 over lambda minus log of s dx, and I divide by that outside. And the reason I do this is I've multiplied by 1, but now this is just the other way of writing an exponential random variable. So what will this integral equal? Yeah, just equal 1 because it's a probability distribution. So because it's an exponential, it integrates to 1. So the lambda comes in down below, and we get 1 over 1 minus lambda log of s. And that will be the generating function of the exponential.
Always?
Mm-hmm. And notice that we need log of s to be less than 1 over lambda. Otherwise, this makes no sense. Okay. Any questions on what we've done up till now? So we've calculated the exponential, and so if you had two different exponentials with parameters lambda 1 and lambda 2, the exponential of x plus y is not going to look nice in terms of these exponentials. So here's a nice theorem. If x and y are independent, then the generating function of x plus y at s is the generating function of s of x at s, generating function of y at s. So the generating function of the sum is the product of the generating functions. The idea is if we start adding more and more random variables together, to understand the sum, it'll be enough to understand one individual generating function to a high power. And I'm just trying to give you a sense of where the central limit theorem proof is going to come from. That's the big result we're going to. So proof. Well, the generating function of x plus y is the expected value of s to the x plus y, which is the expected value of s to the x, s to the y. So what should we do now? So we've got the expected value of a product. What would you like to do? They're independent. Good. So since they're independent, what is the... Yeah, so this is the same as the expected value of s to the x, expected value s to the y. Technically, you have to show if x and y are independent, then so is s to the x and s to the y. All right. So put a little star by doing that. And then this is just the generating function at s times the generating function of y. And we're done. So if you have independent random variables, the generating function of the sum behaves very nicely. Okay. Any questions on generating functions up till now? All right, now we're going to look at moment generating functions. What do you think moment generating functions are good for? Moments, right? Every now and then we do name things correctly in mathematics. It does occasionally happen. This is not another example of sine and cosecant. Right? Moment generating functions. So x is a random variable. Then the moment generating function of x at t is the expected value of e to the tx. Now, the generating function of x at s is the expected value of s to the x. How are they related? Yes?
Is that the same if t is log s?
So t is log of s, or s is e to the t. So if you know one, you know the other. So for example, if x is exponential with parameter lambda, then the generating function of x of s is 1 over 1 minus lambda log s. So what would the moment generating function of x at t be? So we've calculated the generating function. Yeah, it's just 1 over 1 minus lambda t. Our dictionary says wherever you see a log s, just replace it with t, or wherever you see an s, replace it with e to the t. So if I've calculated the generating function, I can get the moment generating function just by replacing any log s with a t. I could also calculate the moment generating function directly. Right. In order for this name to make sense, there should be some connection between the moment generating function and the moments. And that's why we like to work with moment generating functions. Now, if you think back to the example we had earlier today with that terrible function e to the negative 1 over x squared, we had this terrible situation where a Taylor series does not uniquely determine a function. So remember, if we let f of x be e to the negative 1 over x squared if x is not 0, and 0 if x equals 0, then sine of x plus 1701 f of x and sine of x have the same Taylor series at x equals 0. And this is a travesty. Yeah. We should not have such results. The Taylor series should uniquely determine your function. Why did I choose 1701?
It's your favorite number?
It's one of my favorite numbers. Why? So there are two reasons why I like 1701. I'll do another number. I could do 24601. I like numbers that end with an 01. Why did I choose 24601? Miserable, the cultural references that are not being caught.
Do you like Les Mis?
I do like Les Miserables. Alright. Jean Valjean is prisoner 24601. Does it matter what constant I put here? No. Probably could even take f of x to a power. I could probably even do this. Have both. And I will have the same Taylor series. This is to just drive home the need for advanced analysis classes. It's the technicalities like this. Most of you are not going to need to do that. You're going to just use these results, but you should have a sense of what is necessary to prove them. Right? This makes things very painful. So the moment-generating functions, the hope is that if I give you the moments of a probability distribution, that will uniquely determine the distribution. Not the case. So let's recall what the moments are. So if I give you a random variable, so mu n prime is the expected value of x to the n. And this will just be the integral of x to the n times the density. These are the uncentered moments. You could look at mu n, and so the fact that this has a prime should indicate that this is probably not the thing we want to study, is going to be the expected value of x minus the mean to the n. And these would be the centered moments. It's just combinatorics to pass from one to the other. You could expand things out, and you'll get a polynomial here in terms of the nth moment, the n minus first moment, the n minus second moment. Sometimes one thing is easier to compute than the other. So it's just good to know both. All right, so we have the definition of the moment-generating function. So the question is, why do we care about the moment-generating function? Let's expand. So the moment-generating function is going to be the expected value e to the tx. This is going to be the integral from minus infinity to infinity of e to the tx fx of x dx. Do you think this will converge for all t? Not necessarily. If we have a function that's an exponential, let's say this is equal to e to the negative x, then if t is greater than 1, it won't converge. So you need to have more than exponential decay on both sides. Can somebody give me a function that has more than exponential decay on both sides? So I want a function that decays really fast. Normal. Give me another one. Cauchy does not decay fast enough. Cauchy decays only like 1 over x squared. Yeah, take a uniform. Right? Take the uniform on minus 1, 1. How fast is the uniform decay outside of minus 1, 1? Really fast. It's already at 0. So if you take any distribution with finite support, if it only lives on a finite interval, you're okay. But if you're going off to infinity in both directions, you've got to be careful. All right, so let's expand this out. How should I write e to the tx? So I'm going to write this as the sum, n goes from 0 to infinity, of tx to the n over n factorial fx of x dx. And now when I'm doing this, I've got a t to the n, x to the n. The integration is with respect to x, so I can pull out the t. So this will be the integral from minus infinity to infinity sum n goes from 0 to infinity of x to the n fx of x dx times t to the n over n factorial. Well, what does that integral equal? Yeah, just the moments. So this will be the sum, n goes from 0 to infinity, the nth unscented moment, t to the n divided by n factorial. So you just have to remember that there's an n factorial here. So this justifies why we call it the moment generating function. Because if you look at the series expansion, the coefficients of the series expansions are essentially the moments. They differ by having an n factorial down below. Do you care that it has an n factorial down below? You can multiply by n factorial, right? But what's good about having the n factorial down here?
You can get the moments just by taking derivatives.
Well, so good. So one is if you take the derivatives, you'll get the moments, and the n factorials will cancel. But there's another reason why the n factorial is good. It helps with convergence, right? We know t to the n over n factorial converges for all values of t. By having the n factorial down here, even if the moments are growing, we now have such decay, because we're dividing by n factorial, that we have a greater chance of converging. So now we get the moment generating function x of t, I'm just going to write it out really explicitly, is 1 plus mu t plus mu 2 prime t squared over 2 factorial plus mu 3 prime t cubed over 3 factorial. So if you take the nth derivative and set t equal to 0, you will get the nth unscented moment. So if we take the third derivative, this is washed away, this is washed away, this is washed away, we get a 3 factorial, which cancels the 3 factorial. And then everything from here onward, it's at least a t to the 4th, t to the 5th, t to the 6th. They'll all have a power of t left. So this allows us to calculate moments very quickly. If you know the moment generating function, you just have to do these derivatives. Okay. Now, just because we can differentiate doesn't mean we want to differentiate. So I've shown you how to integrate without integrating. I will show you how to differentiate without differentiating. Let's go back to the exponential. So x is exponential with theorem of lambda. So the moment generating function of x, we said is 1 over 1 minus lambda t. So we could start calculating moments by taking derivatives. So the first derivative, we're going to get this is to the -1 power, so we get a negative, this to the -2, and we'll get a negative lambda coming, so that reinforces, so we get lambda 1 minus lambda t to the -2. So mx prime of 0 is lambda. Great, that's what we've calculated for the mean. If we now calculate the second, mx double prime of t, when we take the derivative now, we'll get a negative, and a negative again will reinforce. We'll get a 2 lambda, so we'll get a 2 lambda squared, 1 minus lambda t to the -3. So we get the second unscented moment is going to be 2 lambda squared. And so now, if we wanted to get the variance, it would be mx double prime of 0 minus mx, it's triple x, x prime of 0 squared. So we get 2 lambda squared minus lambda squared is lambda squared. And we would then get the standard deviation of the exponential as lambda exactly as before. All right, so the derivatives weren't too bad in this problem. They could have been worse. Here is another way to do it. We have seen the geometric series many times. We know mxt is 1 over 1 minus lambda t. Yeah. Let's say t less than 1 over lambda. We can expand this with the geometric series formula. This is equal to 1 plus lambda t plus plus lambda t squared plus lambda t cubed. So this is just 1 plus lambda t plus lambda squared t squared plus lambda cubed t cubed. And this is supposed to be 1 plus the mean plus the second uncentered moment over 2 factorial t squared plus the third uncentered moment over 3 factorial t cubed. So we now get the mean is lambda, and we get mu2 prime over 2 is lambda squared, so we get mu2 prime is just twice lambda squared. So we don't actually have to take derivatives. So if you remember how to do Taylor series, or if you have something that's really nice and easy to Taylor expand, then you're in great shape. As an aside, how many of you did multivariable Taylor series expansions? We had more than one variable. Oh dear Lord. I'll have to edit that out. So we have df dx, df dy, then d squared f dx squared, d squared f dy squared, d squared f dx dy, and you have that whole massive nightmare. All right, we're not going to redo all of calculus. So let's say I want to find the Taylor expansion of the sine of x plus y. I know the sine of u is u minus u cubed over 3 factorial plus u to the fifth over 5 factorial. So if you're in a fortunate situation like this, you can actually calculate the multivariable Taylor series expansion very easily. You'll now just get the sine of x plus y is x plus y minus x plus y cubed over 3 factorial. So frequently, if you know a one-variable Taylor series expansion, you can actually get away and calculate the multivariable Taylor series expansion by just choosing an appropriate u. It's unlikely we're going to need to deal with this, but given that so many of you seem not to have seen how to do multivariable Taylor series expansions, it's worth at least mentioning this as a fact. All right. So for the last minute or two of class, what I want to just briefly talk about is standardization. So what this is going to mean is I'm going to give you some random variable x. And frequently we'll study y is alpha x plus beta. And we'll choose alpha and beta so that the mean of y is 0, and the standard deviation of y is 1. So it'll just basically allow us to compare apples to apples. And this is why if you look at probability books, there's only the table of the probabilities of the standard normal, if they give them. Because you can get anything else by just adjusting. This is somewhat similar to the most hated and least remembered log law, the change of base formula. The log of x base b is the log of x base c over the log of b base c. So if you know logarithms in one base, you know logarithms in every base. You only need one log table. Now, for convenience, you will often produce multiple log tables. Because why do you want to keep dividing if you're going to use it so often? Have the logs for 2, for 10, for e, all explicitly recorded. People used to spend their lives calculating values for log tables or trig tables or digit expansions for pi. This used to be a profession. And sadly, there were people whose jobs was to check the people who did. And there was somebody who calculated pi to 700 places, and somebody, when they checked, said, oh, no, you're wrong in place 501. And so from that point onward, all the calculation was wrong. We can automate a lot of this. We can have computers do a lot of this. And the question is, which calculations do you want to do? These are terrific. It means if we understand the logarithms in one base, we get in everything. Over here, we're going to make our random variables nice. We're going to make them have mean 0, variance 1. And that's going to simplify the analysis. All right.